Our project was focused on replicating the movements of a traditional mouse by using hand gestures, and we used the PyAutoGUI package for translating the data to actual movements, and we also after doing data collection, we also implemented machine learning on it. So the output will be a translation of that ML prediction to actual movement on the screen, which we will show later on. For now, I'm gonna hand it over to Grill to tell you a little bit about our data collection process.
After the investigation of the Python Auto GUI package, we have decided to implement 6 movements, including left, right, up and down swipes, and spiral and wave movements. After that, we've started collecting data, including varying speeds to account for the real-world scenario. For each movement, we've collected 30 data points, and for a total of 180 data points. 75% of those data were used for training and 25% were used for testing. After we've collected the data, we have labeled them and uploaded them on GitHub for further processing.
Sorry, I can't attend the meeting. It's nighttime for me, so I decided it's better to record it. So I started with collecting the data. We did 6 gestures, and then me and another teammate, and then we send the data to the machine learning people to analyze it and to build a model from it. In the same time, I built a real-time script of the mouse and the computer. So we had a simple project that worked, that connects the mouse and the sensor to the computer. That worked. Once my machine learning people finished, so I developed a real-time script of Python that connects the sensor to the machine learning model, and it makes predictions. So that's how it looks like on the Python IDE terminal. When I move the sensor, I get predictions of the directions of the gestures as we fed them to the model. And that time I gave it to another teammate to to process this output and to show it to the computer to do the movements we want. When I finished with it, I did this website of the project. To just explain about the project, what we did, how we collected the data, and some data collection video, and all about that. That's it for me. I really enjoyed the class. Thanks.
I'm Vikram, and I'm going to walk you through our machine learning process. So, if you can see my screen, this is our basic structure of the process that we follow. So we started with the basic setup, which is the environment that you need to create to enable the running of the code. The next step was the data setup, where we cleaned and transformed the data to make it into a usable format. Step number 3, which was a very key process, involved exploring the data and performing some basic analysis so that we could understand what kind of data we were dealing with, what were the features that were important to us, if there were any features that could be dropped, if there were any correlations between the features. So this involved performing some techniques like basic PC analysis, performing a t-SNE, plotting the pairs correlations, plotting the correlations, the Pearson correlations. So this gave us a very clear idea as to what would be the best way of handling this data and what further could be applied in terms of the transformation of the data that will allow us to create effective machine learning models that will help us classify our predictor variable, which was the movement type. Okay, so the next step was actually building the machine learning models. So we tried five different models. Model 1 was logistic regression, model number 2 was SVM, model number 3 was random forest, model number 4 was ADA boost, model number 5 was XGBoost. So the process involved training the models on a training data, trying to then run the models to measure their performance in terms of their accuracy, the precision and the recall, and then comparing the performance outputs of all the 5 models and then selecting the best performing model. Well, in our case, XGBoost turned out to be the winner, that too by a wide margin. In fact, initial accuracy we got was more than 80%. So we chose this model, and then the last step of our model selection was to perform some additional model tuning activities, which involved performing a cross validation, a grid search based cross validation that fine-tuned various hyperparameters so that the accuracy could be improved further. And finally, the last step of this process was then we had to save the finalized model in a persistent form to the disk, wherein they could be deployed in any deployment environment and easily invoked and then pass the real-time data. So these are the summary results that we finally got. And as I had mentioned earlier, the performance metrics we used were accuracy, precision, recall, and also the prediction execution time. So our winner, XGBoost, gave us more than 85% accuracy. It had more than 85% precision, more than 80% recall, and the execution time was less than 0.5 seconds. Thank you very much.
Okay, so I'm running the code here. The predicted gesture is shown. We haven't yet defined an idle state. Well, let me rephrase that. We have actually assigned the wave motion, well, yes, the wave class as our idle state. So right now the sensor is not moving, and that's why we see a W on the screen. And right next to it, the number that you see is the percentage of accuracy. Now, so you can see the cursor on the screen here. If I move the sensor here, and the sensor is connected with a wire connection, and if I move the sensor, you can see that the prediction changes and the mouse moves. So I'm moving it in different directions now, and the prediction changes and the cursor moves. So I'm moving it to right now, and the cursor moves to the right, and I'm moving it to the left, and the cursor moves to the left. And I am now going to pass it over to Grill again to tell you a little bit about the future plans, and Vasco to add to that. Thank you.
For future prospects of the project, we think that this setup can be used by a lot of people who have disabilities. For example, a paralyzed person could use a hat embedded with a sensor to steer his wheelchair. By moving or tilting his head left or right, he can use the sensor to control his wheelchair. For example, if he tilts his head to the right, the wheelchair would go to the right, and then if he tilts his head to the left, the wheelchair would go to the left. The sensor could also implement voice recognition to account for the start and stop of the engine of the wheelchair. This way, the person can say stop and the wheelchair would stop, and he can say move and the wheelchair would move.
Hi, I'm going to show you kind of how I try to do the web classification project. Alright, what I did was, I'm still working on it though, not sure if I can finish it by Sunday, but I'll give it a good shot. I built a Django backend, and since Django 3.0 you have ASGI, so you have asynchronous Python code, which has built-in socket support. So before you had to like implement channels in Django, there was like a big hassle. So that kind of made it a bit easier, but it's like a new technology. So I tried around with it, integrated a front end with React, linked the React app with the Django backend, and created an open proxy. In React, I created another bridge with like a native JS library, which can get gyroscope data and acceleration data from people's phone if they give their permission for it, especially on iPhone. The only problem I have right now is that the magnitude sensor is not available for iOS, so Apple's blocking it. So I'm kind of looking for a workaround right now to create a new machine learning classifier just for like a proof of concept, which you can implement in the Django project and see if we can also generate a machine learning model with a big accuracy when we're not using the magnitude sensor. So we're only using the accelerator and the gyroscope, since those are the only two I can get back from the web project. So we'll post a link as well from a web project in our main project repository, and we'll let you know if we can finish it.
So we have managed to successfully establish this prototype. So we now have a proof of concept, and hopefully in the future we can continue on improving this project. Thank you.